Okay. Thanks for coming out, everybody. So I have another speaker here in our Friday seminar series. I am very excited to welcome back to Brown David Charatan. This is a very special visiting speaker for me because David was an undergrad who was at Brown, did some work with me and with Kenny in the in our lab, and was also an HTA for CS2240. Yeah, so this is I think my first undergrad alum returning to give a talk here at the seminar. David is currently a fourth-year PhD student at MIT, which is a wild thing for me to say. Can't believe it's been that long. He works with Vincent Sitzman in the scene representations group and does a lot of work on 3D vision, 3D reconstruction, differentiable rendering, and as you might expect from the name of his advisor's research group, a lot of different scene representations for solving those tasks. So excited to hear what he has for us today. Well, the floor is yours, David. Take it away.
Yes, thanks for the introduction.
All right.
Okay, so I will get started then. So today I'll be presenting Meshtryoshka, which is differentiable mesh rendering for unbounded scenes. And I worked on this with an undergrad in the lab, Daniel. He's now working at Safe Superintelligence, which is Eliasat's first startup. He graduated in May, as well as these others, of which Vincent is my advisor. Okay. So what is the problem that we are working on? The problem is 3D reconstruction. And so this is the problem which you're probably all familiar with, where you take posed images as input, and then as output, you get a renderable model of some scene. And this is the same problem as in NeRF, 3D Gaussian Splatting, and a million other papers. Okay, so what might this be useful for? Maybe video game assets. So if you could take like cars for like this car racing game and just scan them, put them in the video game, and the mesh quality were actually really good, that would be quite convenient. Same thing for virtual reality. So for VR, you want like environments that you can stand in and move around. And for that, if you could just scan them instead of having to build them by hand, model them, that would be great. So yeah, this is what people often cite as sort of the use cases for 3D reconstruction. But if we look at the state-of-the-art 3D reconstruction methods, we have ZipNeRF. This gives you the best quality, or roughly the best quality. And this is a NeRF method. And then we have 3D Gaussian Splatting, which also gives you really good quality. It's a lot faster to render, so this is maybe the best trade-off between quality and rendering speed. But then if you look at these, you can ask, are these actually used in video games and VR? And the answer is, for ZipNeRF, no. And for Gaussian Splatting, the answer is largely also no. Okay, so why is this? This is because NeRFs and Gaussians are both just too expensive to render. So you might be asking, well, aren't Gaussians really fast to render? And the answer is yes, if you have a $2,000 graphics card and your resolution isn't too high, then these are fast enough to render. But if you want to run your Gaussians on a VR headset or a smartphone or something like that, then they're too expensive to render. And proof of this is, so Mark Zuckerberg spent like $1 billion trying to get Gaussians to run on a VR headset. And instead of doing that, they render the Gaussians in the cloud, and then they stream the images to the headset. And maybe the $1 billion were not all spent on this problem, but you get the point. Like, it's difficult to get these things to run fast enough on a headset. So yeah. So what is fast enough? The answer is meshes. And so my claim is that instead of working on NeRFs and Gaussians, we should all be working on meshes. Okay, yes.
Sorry to be a pain.
Yeah.
Are you about to tell me why people tried to work on meshes in the past and moved to soft representations?
Kind of. Sort of. The trajectory of the talk sort of vaguely follows that, but stay tuned. Yeah. Okay, so what does differentiable mesh rendering currently, whoops, this is supposed to play, but it's not playing. There we go. Okay, so this is what differentiable mesh rendering looked like previously. So we have the thing that we want to reconstruct on the right, and we have the result of some state-of-the-art mesh rendering on the left. These are different variants. The details aren't so important, but you can see that actually the reconstruction quality is quite good. But the problem is that this is a masked object, and in addition to that, it's a synthetically rendered object. So we have rendered something in Blender just to reconstruct it again. But that isn't very useful because what we really want is to take real scenes and real objects and reconstruct those. And so what I'm presenting is this, which is a differentiable mesh rendering method that works on real scenes. So here we have NeRF 360 scenes. We have this garden, which you've probably all seen many, many times in the stump, which people don't show as often. But these are actually outputs from our method, and our method can reconstruct these. And you can see that the quality is pretty good. Okay, so now I will tell you about differentiable mesh rendering. And the way that this works is you start with the mesh, and then you render it differentiably, and then you compute a loss, and then finally you backpropagate through this whole process into your mesh. And so we will now consider a toy problem, which is, let's say that we had this initialization, sort of a reasonable initialization for an object. And now the question is, with differentiable mesh rendering, as I have proposed it, can you get this shape? Does anybody want to answer this question? Yes.
No, you cannot,
Okay. Yes. How did you know? The answer is no.
because they have different genus, the two surfaces.
Yes.
One has a hole in it and the other does not.
Yes, exactly. So why is this? The longer answer is if you look at, or a slightly different answer, I guess, is that if you look at what a mesh is made of, it's made of vertices and faces. The vertices are continuous values, the faces are integers, and continuous values can be optimized with gradients, but integers cannot be optimized using gradients. And so, like Daniel said, there is no arrangement of the vertices here, which you can get to via gradient descent, that will turn the sphere into this torus or donut. Okay. So clearly this pipeline is not going to be very effective, and we need to do something else. And what do? We introduce a new, it's also not, yeah, there we go. Mystery step. And what is the mystery step? The mystery step is sign distance functions. And so we take a sign distance function, and then somehow we get a mesh out of that. And then this will solve the problem as we see. So how does this work? Here we have our grid of sign distance values. The positive sign distance values are shown in red. Those are outside of the object. The negative sign distance values are blue. Those are inside the object. And then the sort of near surface area is like white. And then you can run an algorithm like marching cubes to get a surface, and this will be a mesh. And then you can vary these sign distance values to get all kinds of shapes. So you can see we start with this circle, and then we morph it, and it becomes sort of like these two cells, like splitting apart. And you can even put a hole in the circle and make a donut shape. And this is all just by varying the continuous values of the sign distance grid. And you may be wondering, why does my mesh look like a bunch of lines? And that's because it's a 2D visualization. So in 3D, meshes are made of triangles. In 2D, meshes are made of lines. And so a bunch of the visualizations in the presentation will look like the lines, even though it would have been nicer to have 3D. That was too difficult. Okay. So here is our new pipeline. And now the question is, why is this sort of limited to synthetic objects? So we can reconstruct something that looks like this, but this is not like a real world whole scene. Okay. So why is this limited? To answer this question, I'll talk about how the differentiable rendering part of this works. So we'll zoom in on this little patch here, and that will look like this. So we have a bunch of pixels. And to explain this, I'll overlay the mesh vertices. So it's sort of hard to tell with the shading, but if you were to draw the triangles, they would sort of look like this. And now the question is, what happens if I get a gradient from my loss that says that this pixel should become lighter? So remember, the rendering step backpropagates gradients from pixels into mesh vertices. And so if you got a gradient that told you that this pixel should be lighter, then you would push the mesh vertices like this, because the triangle is blue. And so if it covers the pixel less, then the pixel will become lighter and it will do what you want. So that's if it should become lighter. If it should become darker, it's the same thing. Here, instead, you push the vertices the other way. Okay, so that's how this.
So what render are we using?
So this is like in the diff rest.
So rasterizer.
Yeah, rasterizer. And then there's also like soft rest. So like some stuff like blurs the edges and sort of has the same effect.
But NVDiff has this thing where it does take samples on either side of triangle edges to try to do this.
Yeah, it's like analytical anti-aliasing. Yeah, yeah. And then you also get like shading gradients, but I think this is like for the shape, these are the most powerful gradients. But yeah, so these are basically silhouette gradients. So they will sort of nudge the silhouette of the shape to make it the right shape. Yes.
So to be clear, you're talking about updating the sign distance function.
So indirectly, so you update the mesh vertices, and then because the surface extraction, like marching cubes or whatever, is also differentiable, you then backpropagate through the mesh vertices into the grid.
Gotcha. So you need to update the entire edge and then propagate that to the sign distance field, as opposed to just like the part of the sign distance field that corresponds to that pixel.
So I guess like any mesh vertex will be sort of on the edge here somewhere. So a single vertex, like if you place it here, it will backpropagate into like these two values.
Gotcha.
Yeah. Okay.
And that's because you also have the differentiable marching cubes.
Yeah. So and people have like different variants, like flexi cubes, diet10, all of that stuff. But it's like marching cubes is the simplest thing, what everyone knows. Okay. So why doesn't this work? It's because this gives you mostly silhouette gradients, and for whatever reason, the optimization dynamics are such that this is not powerful enough for real scenes.
Because there's no silhouette.
Yeah, I guess
Right.
there's still like a disillusion between shapes, but then so you would think that maybe this could still work, but yeah, for whatever reason. Okay. So what does actually work? The answer is volume rendering. So NeRFs work very well on real scenes. And so the question is, can we make mesh rendering more NeRF-like? And the answer is maybe. Okay. So we're looking for something that looks kind of like this. This is, a diagram of NeRF. We want similar behavior to this, but somehow it should be kind of ray tracing like, and also kind of, whoops, let me go back, mesh rendering like. Okay, so we'll start out with NeRF. In NeRF, you have volumetric density, and so you have this dense, colorful cloud, where for each point you have a density and a color, and then you can ray trace that to produce an image. And so if you have a particular camera ray, or you want to render an image, you will shoot the camera ray into the scene, and then you will take a bunch of samples along the camera ray, and then for each sample you get an alpha or opacity, which is computed from the density, as well as a color. And then in order to compute the ray's color, you just blend these together with alpha compositing. So you take all of your alphas, all of your colors, and then C is the final pixel color. And we've all seen this many times, and we know that it works really well. But in our case, we don't have volumetric density. Instead, what we have is a grid of SDF values. And the problem is that you can't just volume render an SDF grid. And so what we do is, or what we can do is we can take a trick from some of the surface / volume rendering papers like News, Vol, SDF, Unisurf. And first I'll interpolate this, that's easier to visualize. But then we apply a function to this to turn it into volumetric density. And this function is basically just a sigmoid. So you take the red regions, those are positive SDF values, and you map them to 0 density. You take the negative SDFs, you map them to high density, and then everything near the surface is like 50% density, sort of fuzzy. Okay. And now that we have this, we can ray trace. And so this approach minus the grid is basically News, Vol, SDF, Unisurf. But now, if you look at this diagram, you may observe, that most of these samples don't actually contribute to the final output. And there are 2 reasons for this. So the first one is that some of these samples have really low density. So the samples at the beginning of the ray, these basically hit air, and air has a density of 0, and so they don't contribute to the final output. And then there are also samples that are later in the ray, but these are fully occluded. So the density sort of gradually goes up as you go along the ray, or I guess technically the transmittance goes down. And then at some point the transmittance is 0. And so everything behind a certain point is fully occluded, and it does not impact the output. It's not reflected in the output.
Or solid surfaces.
For solid surfaces, yes. That is true. Yeah, so for transparent objects, this is not the case, but we're pretending that those don't exist for now. Yeah. And so in this case, you only need these samples because these are the samples which have non-zero alpha or non-zero density and are not fully occluded. And so the question is there a way that we can only render these samples? Okay. So, and based on this observation, what we are going to do is we're going to switch back to the SDF visualization. And then we're going to run marching cubes on this. But instead of just extracting the 0 level set of the sign distance field, we are going to extract several level sets. So here, let's see, this one is the 0 level set, and then this might be like -0.1, this is like +0.1. But we take a few level sets near the surface, and then we can observe that these samples actually fall on these level sets. So the useful samples, as long as we assume that things are made of surfaces, and we ignore what James said.
Many people do.
Yeah, many people do. In that case, our useful samples basically fall on these SDF level sets. Okay, so with this in mind, what we can do is we can extract the level sets. We can do this because we have an SDF, and then we can intersect these level sets. So we do ray level set intersection, as you can see, and then we sample density and color at the intersection points. And finally, we volume render the samples. And now you may be saying, this is still ray tracing. What does this have to do with mesh rendering? But the level sets are all meshes, and level set intersection, so intersecting a ray and a level set, in this case is the same thing as mesh rasterization. Okay, so here's a diagram that shows this. So here we have level set intersection with the rays. And so what this is doing is for each ray, it's saying what is the closest point on the level set that is hit, and like what is the coordinate of this point. And if you render a depth map with a rasterizer, you're basically doing the same thing. Because this is like the 0 level set of the scene, the surface, you're rasterizing it, you're getting the depth of each pixel. And so you are getting this exact same intersection, modulo like having depth versus XYZ. But from depth, it's very easy to get XYZ, and you can even render XYZ depending on your like shader setup.
Can you just pause for just a second? So I only cast rays through the vertices. Effectively, that's what you're saying.
So this is like the extracted mesh.
Yeah.
So this is a full mesh.
Yeah.
So you're casting rays just like shooting array for every pixel into the mesh. And then it will hit the triangle like somewhere in the middle.
Yeah, okay. And so when we said it's like rasterization,
Yeah,
we still shoot arrays for every pixel.
yeah.
Okay, so we don't actually rasterize.
No, so this is actually rasterization.
Okay.
Because you do it independently for each level set. So
So you just rasterize you just render 3 meshes with the rasterizer.
Yeah.
Right, and you get 3 different XYZ passes. out,
yes,
right?
so this will be clear on the next slide.
Okay, so then I don't shoot arrays.
I guess it's equivalent to shooting rays through pixels, but yeah, you're not actually
That's
shooting
all.
rays through pixels. You are doing rasterization because that is mesh rendering. Okay.
Well, I mean, if you give the stock somewhere else, I wouldn't use the term mesh rendering because you can equally validly render a mesh by ray tracing. Right?
Yeah,
So I would, mesh rasterization is probably more. Yeah.
yeah, I will keep that in mind.
Yeah.
Thank you. Yeah, this is the first time I've given the talk anyway, so you guys are the guinea
Are the guinea
pigs.
pigs?
We're also extremely annoying. But there isn't really a difference.
Yeah, so in practice, it is doing the same thing.
Okay.
But of course, you're only shooting samples near the surface.
Yeah. So if we had like some super high frequency thing that we were trying to reconstruct that was smaller than the size of a triangle,
Yeah,
we would start to notice the difference if we ray traced it versus if we
yes.
rasterized it.
But then in practice, you can also control the spacing of the shells.
Yeah,
The shells tend to get very close together.
and also how many vertices you want in the image.
Yeah, exactly.
Yeah.
And I'll talk about the vertex and trace count as well.
I also imagine that your Z buffer resolution probably plays a factor here, your numerical bit depth of it.
Yeah.
Because as these shells get really close together, you might have Z fighting that happens in the rasterizer.
Yeah,
Yeah.
so we do, well, the shells are rendered separately, so you don't worry about.
Oh, you don't even use a depth pass, so, okay,
Yeah,
depth test, I mean.
yeah.
Just to need a depth test.
Well, you can do that test for each one,
Yeah,
you don't stack them on top.
Yeah.
Yeah.
And because it was easier to unfold, we do this in software.
Right.
So we use close-32. Yeah, that's probably. But yeah, so. Anyway,
Alright.
moving on. So yeah, so now with all that I've said, I will now present the rendering algorithm. So we start with our grid of sign distances, and then we extract some level sets. So here we have innermost level set. This is the most negative sign distance that we extract a level set for, and the outermost one. And then between these, we have a small number of other level sets. So in practice, the total number of these level sets is like 4 or 5. Then we will rasterize these. So this gives you the intersection between this shell and the camera rays for every single camera ray. And you will note that this rasterization is done independently for each shell. So if we have 5 shells, that's equivalent to having 5 NeRF samples near the surface. And you do 5 separate rasterization pulls. Okay. And then we take these intersection locations and sample density and color. To do this, we again use this trick from before where we turn our grid into density that we can sample from. And in practice also, like this interpolation and sampling is sort of done on the fly. So you don't actually instantiate like a dense grid like this. So then we have our color and density samples. And finally, we can just composite these along the rays, just like in NeRF. But again, we only have 5 samples. And the other interesting thing is that in practice, this is just alpha blending like 5 images on top of each other. So that's the compositing part. Oops.
Yeah, this feels like, you said you implemented it in software, on CPU.
Yes.
This feels like it should be able to do this really fast on a GPU.
Yeah, well,
It's just 5 render passes and then alpha blending, right? Like,
yeah,
yeah,
it's implemented in shader slang,
okay.
which is like this CUDA plus additive.
Yeah.
Yeah. But I'll get to that sometime. Yes.
Sorry, I have one clarification. Is it right to think of the level sets like, or like the meshes like some sort of a concentric meshes?
Yeah.
Okay.
Yes. And you might think about why this thing is named Meshtryoshka based on that. Yeah. Okay.
Do you ever get anything weird happening with the level sets due to the genus of the space?
What do you mean by
I
that?
don't know.
Well, it could happen that different level sets will have different genuses, like as you go into the surface,
yeah.
something might split into two components or
Yes.
something like that. That's fine.
Yeah.
Yeah.
The other thing is also like, so this thing I showed about the samples hitting the level sets exactly and it looking exactly like NeRF. This happens if you hit the shells head on. Of course, you can also get grazing angles and then those are a bit weird, but we found that in practice that doesn't really seem to matter. Yeah. Okay. So now I will show you some of these actual shells. So this is for object-centric rendering, where we start with a sphere with moving added to it. And here we have these 4 shells. And you can see that actually they look almost identical. And you sort of really have to squint to see that the distance here is bigger than the distance here. So these are sort of very closely spaced shells. And it's only when you overlay them to produce the final rendered image that you see that there's like some fuzziness in these regions. Yeah. And then, so for synthetic objects, like the classic NeRF Lego, this is what this looks like after like 100 steps of optimization. And here you can see that this basically already looks like a surface. And then it's only if you zoom in that you see that there are slight differences between the shells. So this is also kind of hard to tell, but like look at this, for example. So this is smaller than this. This
That would be useful.
this. Oh, what was that? Sorry.
I think it was David intending to be muted, but it's okay.
Oh, I see. Yeah, and then also in the composite image, you can see that there's still some fuzziness here. Okay. So, yeah, the key insight here is that instead of backcopying through rasterization, you can use mesh rasterization as basically a way of doing sample efficient ray tracing. And it turns out that this works on mid-levels.
Another terminological thing is I would suggest not saying ray tracing for this, because specifically you're talking about ray marching.
Yeah.
The idea that you actually have to take multiple samples along every ray. Because ray tracing is also just
yeah.
one intersection per ray.
Yes, I see. That is another good point.
Yeah.
Yes.
Sorry. So we talked about soft rest earlier. So soft rest, like literally blurs the image.
Yes.
Right. Okay.
Well, it blurs the triangles technically.
It blurs the
Sort of blurs when something is considered inside or outside of a triangle.
But it's blurring them in image space, right?
I don't actually remember how it does it.
I'm trying to relate this to soft rest. I'm trying to think of like blurring in all 3 directions in space, which is sort of what you're doing.
Yeah, I don't remember if it does it in image space. I think it must.
It probably does it in the rasterizer's canonical view volume after perspective projections, which is sort of like an image space, but there is still a depth. No, yeah.
But I've somehow lost. Or maybe I haven't lost this like physique or that.
The Z is there, but it doesn't really matter for the triangle inside outside test. So it's basically like you're doing it.
But here I haven't like lost the Z.
Yeah.
Yes.
Do the meshes have any material properties?
Yeah, so what we do is we have a grid of colors alongside the grid of SDFs. And then we basically get like per vertex color. This that color.
Any view dependent effects?
Yes, because they also have spherical harmonics. So it's like a set of spherical harmonics coefficients at each mesh vertex.
Cool.
Yeah. But it turns out you actually don't need very many. So like degree 1 spherical harmonics. So like DC component +3 is sort of enough. Yeah. Okay. You seem skeptical.
No, it's a separate question.
Well, the other nice thing is once you actually do get a mesh out of it, then you can just do like PBR material optimization as a second pass, right? So.
Yeah.
It's using a surfaces now.
Yes.
Right.
So it's good for surfaces, but not.
But these are going to be mostly surfaces that we're getting at, right? Well, I guess we'll see your results. So
Yeah, so let's see the results. So here, you can see that so for things where there's a lot of constraint by the images, like where you can only render the right thing by rendering the right surface, this will get the right surface. But then if you look closely, you will start to see some cheating where like the depth is wrong. But yeah, so for fine structures, this works pretty well. And here we have the NeRF garden scene. Here you can see if you were hoping to do like PBR materials, like this is cheating.
Not gonna work out so well.
Yeah. But in many for many parts of the scene it's pretty good. So yeah, this is the garden scene.
And then,
Yes.
hey, sorry, what's the initialization?
It is sort of similar to Gaussians. We put like a sphere at like a small subset of the SFF points.
So you start with a big SDF grid, and you basically initialize it as like the SDF of a sphere of a certain size.
So for objects, it is a sphere.
Okay.
And then for these scenes, we take the 0.5 from SFM. And then we
You put little spherical
subsample it.
blobs.
Yeah,
Okay.
exactly. But it's like very heavily subsampled. So it's you'll see it in a later slide, but it's like very, very blobby and blurry.
In the SDA.
Yeah.
Okay, makes sense.
Okay.
Thank
So here is another scene, so you can see it, like it gets these details pretty well. And you can see like the spokes of the bicycle are also mostly reconstructed. The thing that it sort of struggles with is the ground, this like very
Oh,
high
yeah, I
frequency
see that.
texture and like the gravel, it cheats a lot there. And then here we have the flower scene. So the foreground again, it's like pretty good, and in the background it does cheat a bit if you look closely. In like the
Oh, yeah,
part.
you saw.
You put a big shell around the whole thing. Sorry, a big set of distance, like initial distances around the whole thing.
Like sort of like a world.
Yeah.
No, it just like the grid is sort of spatially contracted, stretched out. Yeah.
Oh, in the way that NeRF 360 does it?
Similar, but sort of adapted to the mesh. Yeah.
Okay.
There's a slide about that. So.
Oh, that's great.
Okay. So now I'll be talking about the tricks that you need to make this actually work on real world scenes, because these tricks end up being quite important. And so because this is Halloween themed, we have sparsity and non-cubic grids, spline kernels, course-defined optimization, and finally regularization. And these are the things like apart from this rendering method that you need to actually make it work on NeRF 360. And this sort of engineering effort is where we spend a lot of time. Okay, so first we have sparsity. So in order to run marching cubes, you need to have your whole grid, right? You could run marching cubes on like part of the grid, but in general, you have your whole grid to run marching cubes. And our grid size is 1024 cubed or more. And so if you compute the number of SDF values, that's 1 billion SDF values, and 1 billion times float 32 is 4 gigabytes of memory. And you'll remember that I also said that you have colors for each grid vertex. And so if you have RGB colors, then that's 3 more floats. This would be 16 gigabytes. If you have spherical harmonics, then you have 13 floats per vertex. And so this would totally blow up and not work. And even if you had like an H200 with 140 gigabytes of VRAM, just running marching cubes on 1 billion cells is not as fast as you want it to be. And it's also sort of pointless because like most space is air. So why run marching cubes if it's just air? Okay. Yeah, you could also store them as like float 16.
Oh, I meant like just need occupancy there.
But it's
we
sort of
optimize
just-
continuous value,
Yeah,
but ultimately much still just gonna work.
yeah. But if you want to like interpolate the vertex position along the grid cell, then you
Right, because the mesh, you actually didn't know where the vertex goes.
Yeah, I did. Yeah. Okay. So we have sparsity. The solution here is use a sparse parameter grid. And so what this looks like is we have all of our classical grid cells, and then we only store information near the zero level set. So if the zero level set is sort of like this cell thing from before, we will only store values sort of in a radius around this. And that looks like this. It's a bit tricky because you'll notice that the number of voxels and the number of vertices is not exactly the same, because you always need to surround your voxels with vertices. But basically, we just store parameters at the dots that you see in this image. And this saves you like 90% of your parameters or more. So this is like a big memory savings and a big speed up.
Do you actually build a sparse data structure, or is this like using the sort of spatial hash trick that like a lot of the old school TSDF reconstruction things use?
By spatial hash trick, do you mean also similar to like tiny CUDA and then?
Oh, I'm just thinking of like the early like voxel fusion, like from that.
That's the same.
That
it's
was
the
the
same
same,
trick.
that was the same trick. Okay, I don't know the new stuff very well. Yeah.
So we actually store like all these parameters. So it's like literally just this list of parameters.
I guess what I'm saying is, did you actually build like an octree, or is it like spatially hashed into like a linear array? I'm just curious.
It is, so what we actually do is we have this grid density, but bit packed, and that doesn't take much memory. And then we use that to like query into a flat list.
Okay, yeah, that's what I thought.
Yeah. Okay, so now the question is like, why not use an MLP or a tiny CUDA to store the parameters? And the answer is that with these things, you would pay for the model parameters, but then you'd also pay for n sets of activations, where n is the number of points you actually need. And then you, of course, have to store those n final SDF values themselves. Whereas if you are just storing the SDF values directly, you only pay for this. So there's actually, like, assuming that you need to extract all of your SDF values to run marching cubes, there's no benefit to having any of this stuff. Yeah. Okay, so that's the first trick. Then we have non-cubic grids. So let's say that this is our scene, this is the foreground. And then we want to allocate roughly, oh, and then we have our cameras. Also Halloween themed. And then, well, I'm gonna have to place again because two of these popped up. There we go. Okay. So let's say that we want to allocate a grid, like a uniform grid with roughly this much capacity to the foreground. Then if we want to extend this to the background, we could just extend this grid like this and so on. But the problem is that if we do this for a large space, we will find that we are allocating like 0.1% of the parameters to the foreground. And when people look at reconstructions, they actually care about the foreground a lot. So in practice, you want like roughly 50% of your parameters to be in the foreground and roughly 50% to be in the background. And so what we do instead is we define this uniform foreground grid, but then we sort of define some more grids at the edges. So here you see 4, and 3D this is 6. And then we stretch these out like this. So this is spatial contraction, or like what is referred to as spatial contraction, like NeRF through 60. And the perceived size, like if you are looking from here, the perceived size of like this one and this one is the same. So the trick is that as you go further out, of course, like you don't need as much resolution. And so you can do this. And then the final thing we do is we take these grids, and now these points actually become the same. So like we pull these together, and then we have this. Yeah, so this also makes sure that the angular resolution does not increase as you go further out from the grid. Yeah, but once we do this, we are basically able to allocate about 50% of the parameters to the inside, or to the foreground, and 50% to the background. And the perceptual quality as you go further away sort of remains the same. Okay. The third thing out of 5 that we have is slang kernels. So it's difficult to implement this like sparse grid in PyTorch and sparse marching cubes. So we use slang, and also if you do this in PyTorch, you get many, many trips to GPU global memory. So like every time you do like a simple operation like an addition, you go to GPU global memory. But if you're writing something in slang, then you can fuse all these operations together. And so it's a lot cheaper. And so our solution is to use the slang shading language, which you may not have heard of. It's very, very similar to CUDA. So this is a screenshot of some slang code from the project. And if you have coded in CUDA before, you'll recognize this, like index equals CUDA block index, blah, blah, blah. So there's actually mostly a one-to-one correspondence between slang and CUDA. The key difference is that slang has autodiff. So you can add this decorator or a tag to your functions, and then you can call this. So you can get a backward mode gradient or backward mode autodiff. And so this makes it very easy to try out differentiable things because you don't have to worry about getting the derivatives right. Okay. And now I have a fun fact for you, which is that slang uses 32-bit tensor indexing. And why is this relevant? Because it means that if you have a tensor of float 32, the maximum addressable size is 2 to the 30. And so while trying something out, we had a tensor with more than 2 to the 30 elements. And we got this, which is very spooky. Yeah, you don't want to see all these glitches. Like this weirdness. Okay, but there's a workaround for this as well. Okay, and then so the next trick we have is course-defined optimization. This is a classic for any graphics and vision thing. This makes training faster, and it also keeps triangle count manageable. Because if you start with a fine resolution, then you get all of these like crinkled surfaces. Whereas if you start with a coarse resolution, you get smooth surfaces, and you subdivide them and they sort of stay smooth. And so here's a video of our optimization. You can see we start with this SFM point cloud initialization that I was talking about earlier, and then we subdivide. And at each subdivision step, you can see that the quality sort of takes a jump. And then it sort of like hangs out around that quality until the next subdivision step when there's another jump. So here's another one. And one interesting thing is that it only makes sense for the loss to add certain parts of the scene at higher resolutions. It's like at a low resolution, it doesn't make sense to represent the spokes of the bicycle because the loss is higher if you just skip them entirely. And so for fine details, you get this growing effect, which is maybe sort of similar to silhouette gradients, but I guess in practice, this works on these kinds of scenes. Yeah. Then here we have flowers. This is another one. I think this one is sort of one of the more boring scenes in NeRF 360. There's not as much to see. Everything sort of looks the same. And I'll let this play. And then we have the countertop scene. And you can see actually, if you look at this pasta bag, this is not a solid surface, and so it struggles with this. And then also the Brita filter here isn't as bad, but you can see that because it's designed for surfaces, those things are not great. Okay, and then finally we have regularization. So the regularizers that we have are smoothness plus binary intensity loss. And what we actually don't do, even though this is presented as the SDF, is we don't have an iconal loss. So I've been lying to you this whole time. These things are not actually SDFs. It is helpful to understand them as SDFs, but because enforcing an iconal loss on a grid doesn't really work that well, we found that actually if you drop the iconal loss, it works better. But our other regularizers fix this problem. So if you don't have any regularizer, then you'll see that the surface here is quite well constrained. So like this all looks good. But then you don't have any losses that update the stuff inside the shape. And so this is like an unconstrained SDF, and this just sort of becomes fog. And so we have this binary opacity loss, which basically says that the SDF should either be high or low. And that way this will sort of clean up all the fog and make this hollow as it should be. Yeah, but I think you sort of can't get around this because the area inside the shape is unconstrained by the rendering loss. So you need something to get rid of the fog. Okay, that fog. Okay, so now I'll talk about some limitations and perspectives on this in future work, very briefly. So the biggest limitation here is the number of vertices and faces. I'm going to show you a plot from our tensor board, and you may notice this is the number of faces. As we hit the last few steps of optimization, the number of faces is 236 million. So this is an absolutely absurd number of faces. And this is spread across 5 level sets. So actually the 0 level set, which is what you use in the end, is not this bad. It's like 45 million faces-ish, a fifth of this. But this is a huge number of faces. And so there is a real cost in spawning so many faces. Yeah.
You say it's ridiculous, but how many faces do we need to represent complex geometry without those scenes?
Yeah, I think a large number, but maybe not infinity. Because like the problem is that even like flat surfaces are just very, very densely calculated. So if this were more like a mesh that human made, you would not need this many.
Thanks.
Yeah. Okay. Then the next limitation is the optimization dynamics. So the optimization dynamics here are a bit trickier than with NeRF. Like NeRF is very nice because you always control the sample spacing, and you have gradients from everywhere in space, even though like a lot of stuff is just there or like occluded. So the optimization dynamics here are a bit trickier than with NeRF. And then also, we don't actually have a valid SDF, like I said, because enforcing iconal loss under grid sort of gives you locally correct gradient magnitudes for the SDF. So like you could add an iconal loss and it would be satisfied everywhere, but it would not actually give you a valid SDF. But yeah, so our SDF is not actually valid. And so the result is that you get these very, very closely spaced shells. So what we want is that we can sort of control the fuzziness here so that we can schedule it, sort of start out like coarse and fuzzy and then get to a sharper shape. But in practice, that is very hard to do. And then finally, the metrics are a bit worse than NeRFs and Gaussians. So like this is a mesh-based thing, and it lets you render real-world scenes, but you, in its current state, probably would not use it because NeRFs and Gaussians just gave you better quality. Okay, and now finally, you may know that there is this whole line of work on baking to meshes. So baking in this case is you take your like NeRF or your Gaussians, and then you just extract a mesh and maybe optimize the mesh to get you the same scene. But I will claim that baking is bad because 1, it tends to be very time consuming, 2, it's not very elegant. So if you could just optimize a mesh in the first place, not have to first optimize a mesh or optimize, sorry, a NeRF, then extract a mesh and then optimize the appearance of the mesh and then do like 3 other steps. It would be better if we could avoid that and just optimize the mesh. And then last of all, if you could get this rasterization-based stuff to work really well, then you could take advantage of hardware acceleration for rasterization during training. So there's this potential for getting maybe a speed up or like using taking advantage of the hardware work. Okay, and on the time point, so this is the state of the art of baking. It's called binary opacity grids. I will give you a rundown of the pipeline for this. So for this, you train a zip NeRF. That already takes a while. Then you do 25,000 steps to binary of optimization to binarize the opacity. So to make the opacity go to either 1 or 0 everywhere. Then you extract a mesh. And then because this mesh has hundreds of millions of triangles, actually more than our method, you need to simplify it. And simplification on such a huge mesh takes about 4 hours. And then you do 100,000 further steps of optimization. And they don't actually tell you how long this optimization takes. And the code is not public because it's from Google. Whoops. But if you assume like 10 iterations per second for the optimization, this will still take 9 hours. So if the optimization were instant, it would be like 4 or 5, I guess. If this were a bit slower, it would take longer, but this takes a long time. And like by contrast, our method takes like roughly 4 hours, which is still, I mean, not great compared to instant NGP and like 3D Gaussian splatting and whatnot, but it is a lot faster than baking.
Should this fly if you write it in Harvard?
Hmm?
Like I said earlier, shouldn't this fly if you write it in Harvard? Shouldn't you?
Yeah, I mean, we did not optimize this as well as we could have, so there's like probably a lot of juice left to squeeze. Yeah. Okay, so future directions. So we use a uniform grid, so it's a sparse grid, but it's a uniform grid And then we apply this like spatial contraction stretching thing. But it would probably be better to use an adaptive data structure. So you could use like an octree, or you could even use like Voronoi cells plus marching tetrahedra or something fancier like that. And then you can try to get sort of more efficient use of triangles for like large flat surfaces, or just regions where you don't need a bunch of super triangles. And then also the optimization dynamics here could be improved a lot. So one thing you could do, for example, is because you're just optimizing raw SDF parameters, you could extract a zero level set at every step and then compute the distance to that level set. And that way you could have like a valid SDF at each training step. And we tried this a tiny bit. It turns out that the round trip between Marching cubes and like creating a zero level set and then computing the distance to that is not like something consistent. So that's a bit tricky. But if somebody could find a way to create a cycle consistent way to go from zero level set to SDF grid and back, then you could probably make the optimization dynamics for this a lot better. And then anti-aliasing. So we end up with a lot of really, really small triangles, and that comes with all kinds of issues. So if you could find a way to sort of push a single pixel's gradients into many small triangles, then that would probably improve this a lot. Okay, and now finally, I have a question, which is, could mesh rendering become competitive, or mesh rasterization, I should say. So here we have this grid of stuff that people commonly do in NeRF land. And so for volumes plus ray tracing, which should be, I guess, marching, we have NeRF. And this is like wildly successful. This works really well. For volumes plus rasterization, we have 3DGS. For ray tracing plus surfaces, we have NUS. So, you know, this is surface-based, it's optimizing SDF, but it's doing it in this NeRF style with the trick that I talked about. But there really isn't like a standout thing in this category. So people will take like Gaussians and make them flat, and then like have losses that encourage them to be surface-like. There is now 3D triangle splatting, which is also sort of meant to be surface-like, but nobody's actually optimizing a surface with rasterization. And so this project was sort of an attempt at filling this gap here. And I think we sort of have a proof of concept, but there's clearly a lot of work left to do. But I think like if somebody optimized this and worked on this, maybe there could be the missing quadrant that could be filled. Yeah.
And the NVIDIA work doesn't fit into here because they're using TEDs, and so it's like a volume based.
You mean like NVIDIA for us?
Like DM test and that kind of stuff.
Yeah. I guess that stuff, they only show it on objects. So that's the thing I was talking about for how if you're doing like mesh rasterization and edge gradients with anti-aliasing.
So that does occupy this quadrant, but not for
But
natural scenes.
Yeah,
right?
So it's like there's a third axis of this.
Right, yeah.
Yeah, this is like for real scenes for practical applications. Nothing really optimizes this quadrant. Yeah.
How fast is marching cubes?
How fast? So if you do it sparsely, it can be pretty fast. I would have to look up the exact step time, but it's like faster than you think. So like if you were thinking this takes like several seconds per forward pass, no, it's like on the order of milliseconds and not like seconds.
Have you like profiled how much of each step of your pipeline is contributing to the cost?
Yeah, so I think in the end for high resolution, it's like half marching cubes, half rendering. But we also, so we started out by taking the 3D Gaussian Splatting rasterizer, and there's a slam version of this, and then we sort of modified it to use triangles because we sort of settled on this exact method later. So like that the rendering part could definitely be sped up, but with something that looks like the Gaussian Splatting rasterizer plus like sparse marching cubes, it's like about 50-50. I think. I would have to check and look at the yeah. And then finally, why is it actually called Meshtryoshka? It's because the concentric mesh shells kind of look like these Meshtryoshka dolls. And that's it.
Cool. Yeah, time for maybe a couple of additional questions people have.
Yes.
You probably addressed this before. Sorry, I was late for your talk. But what are the key benefits of having a surface? Like, what do you use it for?
So I mean, a surface would be good if you had like physical materials in general, and like a surface, like meshes are of course faster rendered, they're more useful than like volumes. In practice, this does not actually give you higher surface quality. So this suffers from the same like depth ambiguity problems as NeRFs and Gaussians. So yeah, so I think surfaces in general would be good for many things. This doesn't actually give you great surfaces though.
Sorry?
Sim?
Sim?
Simulation. Any other questions? Yes.
Maybe I've asked too many questions, but a bunch of different people have proposed like shell-like representations, right? Like Meta had one.
Yeah, the fuzzy.
Yeah. And so, is the, how can I say, some people keep the shells around as well, right? But here we're only using the shells to find new things, right?
Yes. Yeah. And then it turns out actually that if you compare the like, known quality between the shells, like 5 shells and just the 0 level set, because this thing really prefers to squeeze the shells together, like the final render quality is basically identical. Like it's like 0.1 dB of difference in PSNR or something.
Okay.
So this really like the natural tendency for this to converge to a surface of all the shells.
Okay.
Yes.
So, thanks for the talk. I'm wondering, like, would it have made the problem easier if, like, we're only looking for the stuff, we don't care about the grass and all of the other stuff, like, or like, I guess, are those things kind of adding to the difficulty here? Like, would the results of the stuff be better if those things, like, we don't need them? Like,
Yeah. The background tends to be a lot harder, and there are a few reasons for this. So there's like, you need to pick how you allocate the parameters between the foreground and the background. And then the background also tends to have much lower quality supervision. So at the foreground, you see things from many different angles, and so you can constrain the surface very well. But for the background, you have a much smaller baseline. So you tend to see things from roughly the same angle, and we get there's like left right difference. And that's a lot harder to optimize. And then the other thing is, if you have something like a mesh or an SDF, you tend to place a lot of junk behind what you can't see. So the background has a lot of like fully occluded regions, and so you have to have good regularizers to get rid of the fog there, especially if you're explicitly instantiating all of the fog as triangles, as we do.
thanks.
Yeah.
All right, I think we should probably wrap up for now, but folks are free to ask questions offline afterwards. Let's thank our speaker one more time.